Hello everyone, my name is Joseph. I'm from Mason ECA. Today I'm welcoming you for the seminar presentation based on the non-volatile memory technology for electronics. These are the table of contents that we have to discuss about the basics of non-volatile memory technology, then the history and the different types of non-volatile memory that are available, and the the technology, the technical level of the different types of non-volatile memory, and then the advantages and disadvantages, and then the applications lab. Moving to the introduction. Basically, we know that the memory can be divided into two, volatile and non-volatile, and the memories are the essential part of different variety of electronic system during these years. And memory technology for electronics is advancing rapidly with the new technologies emerging that offers significant improvements in density, speed, power consumption, and cost. As these technologies continues to develop and become more affordable, we can expect to see significant improvements in the performance and capabilities of electronic devices. Moving to the history. In 1967, the floating transistor is developed at Bell Labs. In 1971, the first non-volatile memory device, a read-only memory chip, is developed at Intel. In 1975, the first programmable non-volatile memory device, EEPROM, is developed at Intel. EEPROM is electrically programmable read-only memory. The flash memory chip is developed at Toshiba in 1980, and the first commercial memory chip is released by Intel in 1986. And in 1990, the flash memory begins to be widely used in consumer electronic devices. Between the 1996 and 2005, the flash memory becomes the dominant type of non-volatile memory used in portable computing devices. In 2010, new types of non-volatile memory such as phase change RAM, resistive random access memory are developed, and we all know about in nowadays non-volatile memory is increasingly being used in new applications such as AI. And moving to the basics of NVM, that and everybody has the query that about the what is an NVM. NVM is simply is a type of electronic memory that can retain data even when power is removed. And the non-volatile memory is a byte addressable and random access memory for computers that retains data even when the power is off. And byte addressable memories facilitate access to data at the individual byte level. Non-volatile memory is a used in wide range of electronic devices, including computers, smartphones, tablets, and digital camera. In addition to the basic principles of non-volatile memory technology, engineers also need to be familiar with the latest advances in this field. Non-volatile memory technologies are emerging all the time, and the engineers need to be able to evaluate these new technologies and determine how they can be used to improve the performance and capabilities of electronic devices. Next, the non-volatile memory can be addressed in two ways. First one is electrically addressed systems, and second one is mechanically addressed systems. Non-volatile memory and falls into two categories. Either it is electrically addressed or mechanically addressed. And the electrically addressed systems are further categorized by right mechanism and tend to be more expensive comparative to mechanically addressed system. And electrically addressed system have systems are faster and have less capacity than their mechanical addressed counterparts. The examples for the electrically addressed system is flash memory and FRAM. Mechanically addressed systems have larger storage capacity than electrically addressed systems. Examples for the mechanically addressed system are hard disk, magnetic tape, and optical. And then why non-volatile memory technology used in different kind of applications or different kind of devices, etc. And the first factor is that none other than the non-volatility. Non-volatile memory retains data even when power is removed. This makes it ideal for use in devices such as smartphones, laptops, which need to be able to store data even when they are off. And durability. Second one is the durability. Non-volatile memory can withstand a large number of read and write cycles without degrading. Third one is the performance. It, in non-volatile memory can read and write data much faster than the traditional volatile memory technologies. Ideally for use to it makes it ideal for use in applications such as high performance computing and these are the moving to the process involved in data storing and retrieving in non-volatile memory. Everybody has the query that or have the doubt that how it stores data in non-volatile memory and how it retrieves the data or how access the data even when they are powered or off or then when the device is when the device is restarting, how it accesses the data, how it retrieves the data, and the first steps involved is when the data preparation. The data is stored by converting it into a format that compatible with the specific non-volatile memory technology. Sometimes this may involve encoding the data and compressing it or breaking it down into a suitable levels. And the second step involved is addressing memory cells. Each non-volatile memory cell has a unique address that identifies its locations within the memory array. The data is enrouted to these addresses, determining where the information will be stored. Third step is programming memory cells. The programming process involves altering the physical states of memory cells to represent the data bits. This may involve trapping electrons in a floating gate a transistor, modify the resistance of material, or changing the polarization of anything material. These step is very much important. And moving to the next process, that the verification and error correction. After the programming, the stored data is verified to ensure its accuracy. Error correction mechanisms may be employed to detect and correct any discrepancies that arises during the programming process. That when the data can be sometimes the data can be uh, have the error or that the data must be data can be lost in sometimes. The next step is power removal. Once the data is successfully stored and verified, the non-volatile memory can disconnect from the power source without losing the stored information. That make it not volatile. And data access the sixth step is the data access and retrieval. When the data needs to be retrieved, the non-volatile memory is powered on, and the stored data is read by sensing the physical state of memory cell. The data is then decoded and converted back into its original format for it. Basically, these six steps are the basic step, or the general steps involved to store and retrieve data in non-volatile memory. This can be changed according to the non-volatile technology that used in different level. These are the different types of non-volatile memory that today we have to discuss about. First one is flash memory. Second one is ferroelectric RAM. Third one is magnetic RAM. Third one is phase change memory, and fifth one is resistive RAM. The these five memory types of memory can be classified by the physical mechanism. And first one is charge-based non-volatile memory is flash memory and ferroelectric RAM. The second one is phase change in non-volatile memory, phase change RAM and resistive RAM also involved in this section. And third one is magnetic RAM that also uh, into the magnetic non-volatile memory. Moving to the flash memory, let's focus on the let's let's start with the flash memory. Start with the flash memory and uh, today non-volatile memory are highly reliable and can be programmed using a simple microcomputer which virtually in every modern electronic equipment which are expected to replace the existing memories. Um, Among them, emerging non-volatile memories are now very captivating, and the um, flash memory is basically a MOSFET non-volatile device that can be electrically raised and programmed. It is a technology that is primarily used in memory cards and flash drives for general storage and transfer of data between computers and other digital products. Since the invention of the transistor, non-volatile semiconductor material, non-volatile semiconductor memory have the most important invention in the electronic device field. And the floating gate memory was used to store the information and a tunneling current for programming and erasing operations. The charge is injected into or removed from the floating gate, and the floating gate remains in that state. And even after power is removed, which means that the flash memory is non-volatile. And the flash memory can be divided into two, that is NAND flash and NOR flash. And the two major flash types are dominant in the memory market also. And NOR flash has lower density but a random access interface, while the NAND flash has the higher density and interfaces access through a command sequence. Their corresponding structures are shown in this figure, and the structure or the structural representation of NOR and NAND memory cells. And Intel is the first company to introduce a commercial NOR type flash chip in 1988, and the Toshiba were released the world's first NAND flash in 1989. Mm, and moving to the cell structure, flash memory is built from the memory cells arranged in a grid. Each cell stores data as electrical charge, typically in the form of electrons in an insulated gate. And the two main types of flash memory cells are NAND and NOR. Mm, the NAND flash and NOR flash can be compared that is possible to distinguish between the NAND flash memories and NOR flash memories. In Firstly, in NOR flash, cells are connected in parallel to the bit lines, which notably allows the cells to read and programmed individually. The parallel connection of NOR flash cells resemble the parallel connections of transistor in a CMOS NOR gate architecture. On the other hand, in NAND flash, the cells are connected in series, resembling in a AND gate. The series connections consume less space than the parallel ones, and reducing the cost of NAND flash. It does not by itself prevent NAND cells from being read and programmed individually. And examples for an NAND flash memory is used in high capacity data storage devices like SSDs and the USB drives, but in no flash memory used in embedded systems for firmware storage. These are the basic comparison between the NOR and NAND cells, and uh, in the memory size of NOR cell is less than or equal to the 512 mbit, and NAND cell 12 gigabit. And the program time involved in NOR cell is 9 microseconds per word, but in the NAND cell is 400 microseconds per page, and the write time is 1 second per sector in NAND, 1 millisecond per sector, and the read access time is less than 18 nanoseconds. In NAND cell is 20 microseconds. Output parallelism is in NOR is byte or word or B word, but in NAND byte or word. And the access method is random in NOR cell, and the is sequential in NAND cell. Uh, These are the basic write and erase operations that allows in flash memory. Data can be written to flash cells by applying a voltage to them, and that can be raised by removing the charge. However, flash memory cells have a limited number of write erase cycles, which can affect their lifespan. Moving to the next non-volatile memory technology, that is ferroelectric RAM. Ferroelectric random access memory is a type of non-volatile memory that uses ferroelectric materials to store data. Ferroelectric materials are the materials that have a spontaneous electric polarization, which can be reversed by applying by an external electric field. Uh, if RAM maintains data without any external power supply, it achieves by using a ferroelectric material in place of conventional dielectric materials between the plates of capacitor. When an electric field is applied across the dielectric or ferroelectric materials, it will polarize, and while the field is removed, it will depolarize. Moving to the basic structure of FIRAM cells. FIRAM cells typically consist of ferroelectric layer between two electrodes. The ferroelectric layer is typically made of lead silicate titanate and ferroelectric material that is known for its high polarization and endurance. The electrodes are typically made of metal or polysilicon. And uh, moving to the operations that involves in ferroelectric dam. First one is to read and FIRAM cell, a small electric field is applied to the electrodes. The electric field switches the polarization of ferroelectric layer, which changes the resistance of cell. The resistance of the cell is then measured to determine the stored data. To read an FIRAM cell, to write a FIRAM cell, a large electric field is applied to the electrodes. The electric field switches the polarization of ferroelectric layer to desired state. The ferroelectric layer will remain in the state even after the electric field is removed. Next one is the MRAM. MRAM basically based on memory cells have two magnetic storage elements, one with a fixed magnetic polarity and the another with a switchable polarity. These magnetic elements are positioned on the top of each other and but separated by a thin insulating barrier as shown in the cell structure. Moreover, scientists defined a metal as magnetoresistive if it shows a slightly change in electrical resistance when placed in a magnetic field. By combining the high speed of static RAM and the high density of DRAM, proponents say that the MRAM could be used to significantly improve the electronic products by storing greater amount of data enabling it to be accessed faster while consuming less battery power that existing electronic memories. Um, Technically, it works with the state of the cell, which is sensed by measuring the electrical resistance while passing a current through the cell because of the magnetic tunnel effect. The moving to the operation, uh, if the both the magnetic moments are parallel to each other, then the electronics will be able to the tunnel and the cell is in the low resistance or on state. And however, if the magnetic moments are anti-parallel, the cell resistance will be high. The memory characteristics of MRAM of writing and erasing are fulfilled by a passing current through the right line to induce a magnetic field across the cell. Moving to the next non-volatile memory is phase-changing RAM. PCM is a phase-changing memory is a non-volatile memory technology stores data by using the properties of phase-changing materials, typically a charcoal granite alloy, which can exist in two distinct states, amorphous and crystalline. Amorphous states also known as low resistance state and crystalline states known as the high resistance state. These two states represent binary in binary data, zeros or one. Uh, as you all know about PCRAM, its uses in the differences in electrical properties of amorphous and crystalline phases of a amorphous phase and and crystalline phases of diagonal to store a memory state. When the sarcogenide is in the amorphous phase, the resistance significantly higher than when it is in the crystalline phase. This reversible electrically inductor resisting switching, which results in a stable phase change. These are the operations that used in phase change memory. First one is write the data in PCM to a PCM cell. A high voltage pulse heats the phase change material. Rapid cooling then determines whether the material become amorphous or crystalline. Reading data from a PCM cell involves measuring the resistance of the materials, which depends on its phase. The resistance value is then interpreted as the stored data. Moving to the next non-volatile memory is resistive RAM. Resistive RAM are the cells typically made of MIM structure, metal insulator, metal structure. The insulator layer is the material in which the resistance tends to store the data. When a voltage is applied to the resistive RAM cell, it causes a filament to form in the insulator layer. Uh, the theoretical mechanism of resistive RAM shows filamentary type resistive switching, where the oxygen vacancy is considered to form conductive filaments in the resistive materials are shown in the figure. The formation and the disruption of these filaments are thus the mechanism responsible for on-off switching in the resistive RAM devices. The key issue is therefore to reveal electronic roles in the formation and the disruption of vacancy filaments. Resistive RAM can be switched between the low resistance states and high resistance states of the resistive material by applying voltage to the electrodes. Mm, uh, Resistive RAM is a disruptive technology that can revolutionize the performance of products in many areas, from consumer electronics and personal computers to automotive, medical, military, and space. Among all current memory technologies, resistive RAM is uh, attracting much attention since it is compatible with the conventional semiconductor process. Uh, Also, memory star-based SSD RAM is one of the most promising emerging memory technology. Moving to the read, write, and erase operation to write data to an SSD RAM cell. A voltage pulse is applied to change the resistance states of the material. High resistance represents one binary state, while low resistance represents the other. Reading data from resistive RAM cells involves measuring its resistance to determine the stored data. The resistance states corresponds to the binary value, and then the erase a voltage of the positive polarity is applied to the resistive RAM cell, causing the filament to break. This resets the cells to its original high resistance state. These are the applications that we have to see in different day-to-day life, in industry and transportation, for enterprise storage, mobile phones, mass storage, memories, embedded MC for smart cards like SIM card, ID cards, etc. These are the basic applications of non-volatile memory technology in main memory in computers and mobile devices, storage for wearable and IoT devices, cache memory for processors, neuromorphic computing, and also used in analog circuits. These are the factors mainly affecting the non-volatile memory technology. Let's see the comparison between the different memory technologies. Uh, these are the factors, and first one is the endurance. In Ethereum is uh, high endurance that available in Ethereum and in MRAM. But in resistive RAM and pasting RAM is typically in medium level, and the cell size is comparatively large among four of them is 50 to 20. Uh, in RAM cell, it varies from 6 to 40, but in resistive RAM is medium. Also in PC RAM, about 6 to 12. And the write speed of the FRAM is 100 nanosecond. In MRAM is 10 nanosecond. In SSD RAM is 75 nanosecond, and PC RAM is 75 nanosecond. The power consumption is comparatively low in FRAM, but in MRAM is high. Uh, High or low according to the application level, and the resistor RAM is low, and PC RAM is the power consumption of PC RAM is low comparatively. These are the future trends and developments that are available in non-volatile memory technologies. Germanium thin-transistor non-volatile memory is a promising alternative material for use in advanced technology now because it exhibits symmetrically mobility of holes and electrons embedded. Non-volatile memory is essential in electronic devices with integrated circuit technology, including future germanium-based technology. The germanium twin transistor exhibits high programming and erasing speed and satisfactory reliability. Moreover, the mass and the fabrication process of these germanium twin transistor non-volatile memory are identical identical to those of germanium channel FinFETs. Thus, germanium tin transistor non-volatile memory is a promising candidate for embedded non-volatile applications in the future high performance. These are the non-volatile company list, non-volatile memory making company list with the basic. These are the manufacturers that are available in non-volatile memory technologies. Mm, Memory technology segment, and we are looking ahead as with the most technology. The uses and applications for non-volatile memory continues to evolve and expand. The demand for the subsequent growth in memory for storage and the other applications will be increased as this technology is becoming popular in digital world, in smartphones, cloud surveys, etc. The recent developments in non-volatile memory space includes CB RAM, is conductive bridging RAM, and the domain wall or racetrack memory, millipede non-volatile memory, NRAM, NanoRAM, and Sonos. Sonos is silicon oxide nitride oxide silicon, a cross-sectional structure of MOSFET for non-volatile memory. Let me conclude the overall presentation that non-volatile memory technologies have a bright future since every end-use application needs to store some parameters or some amount of data in the onboard non-volatile memory to enable it to function. The upcoming non-volatile memories are the big hopes for a semiconductor memory market, which provides memories for systems to run with the flexibility, reliability, high performance, and low power consumption with the low cost in every electronic application. Overall, non-volatile memory technology is an essential area of study for electronics and communication engineers. By understanding the different non-volatile memory technologies available, how to select the right non-volatile memory technology for a particular application, engineers can design and develop more efficient and reliable electronic devices. These are the references that I have chosen to make the presentation, and thank you.